There are places in the universe where the laws of physics as we know them are on the verge of oblivion, where time warps and space bends. Centuries ago, an apple fell, and with it, the seeds of Sir Isaac Newton's gravitational theory were sown. It was a simple truth. An apple attracted to the earth. But it revealed a cosmic meaning that binds the universe together. Within that meaning, however, lurks a large gap so strong that no known particle can leave it. This is the realm of black holes, cosmic mysteries that have stumped astronomers, physicists, and philosophers for decades. Imagine, if you will, a maelstrom in the fabric of space-time so powerful that even light cannot resist its pull. This is the event horizon, the point of no return. It is here at the very heart of this cosmic anomaly that the concept of singularity is found, the point where mass is believed to shrink to infinite density and the laws of physics collapse under the weight of its impossibility. But what if everything we used to think about these dark giants is only part of the truth? What if the singularity, that point of infinite density and zero volume, is not the inevitable end of a black hole's center? Recent research has begun to lift the veil on this mysterious phenomenon, questioning the very notion of a singularity and suggesting a reality far more complex and even more enigmatic. Join us to try to make sense of this issue together. At the very heart of the 20th century, as physicists delved ever deeper into the fabric of the cosmos, a groundbreaking theorem emerged that cemented its place in the annals of physics. Sir Roger Penrose, a visionary British physicist, introduced the world to Penrose's singularity theorem, which challenged our understanding of the universe and its most mysterious entities, black holes. This theorem, presented in 1965, uses the mathematical foundations of the general theory of relativity to make a profound statement about the nature of black holes and the inevitability of singularities in them. Penrose's theorem relies on an underlying principle of Einstein's general theory of relativity, which describes gravity not as a force in the traditional sense, but as a curvature of space-time caused by mass and energy. According to the general theory of relativity, massive objects such as stars and planets warp the fabric of space-time around them, affecting the motion of objects and even the path of light. Penrose's singularity theorem states that under certain reasonable conditions, in particular the presence of what he called a trapped surface where light rays converge rather than diverge, a singularity, a region of the infinite curvature of space-time, must form inside a black hole. This locked surface marks the point of no return, beyond which all paths inexorably lead to the singularity, the place where the known laws of physics cease to operate. One of the most striking consequences of Penrose's theorem is the concept of geodesic incompleteness. In the context of space-time, a geodesic is the shortest path between 2 points, like a straight line in curved space. Penrose's theorem suggests that inside a black hole, some of these geodesics cannot be infinitely extended into the past or future, indicating the boundary of space-time itself, the singularity. Imagine you're floating in a kayak on a calm, wide river, and it represents the universe, the river's current, its constant flow and direction, reflect the paths in space-time known as geodesics, along which planets, stars, and light move due to gravity. As you swim further, you approach an area where the river current becomes increasingly turbulent. Ahead is a huge hidden waterfall shrouded in mist. This waterfall looks like a black hole, and the point where the water begins to fall downward resembles an event horizon, a boundary beyond which there is no return. As the water approaches the falls, the currents that used to flow parallel begin to converge and accelerate toward the edge of the falls. Despite the speed of the water and the strength of the river, neither can escape the pull of the waterfall when it reaches the cliff. This convergence of the river's currents at one point, but never reaching a stable end, illustrates the concept of geodesic incompleteness near a singularity inside a black hole. Near the horizon, a photon kayak trying to swim directly against the current just stays put, no matter how much you try, but you never swim anywhere. The currents of space directed inward completely neutralize your motion. Inside the horizon, the cosmic waterfall falls faster than the speed of light, taking everything with it. The water, representing the paths of particles and light, does not simply stop or shrink. Rather, the nature of the river's space, the landscape itself, changes dramatically at the waterfall. The paths of water are forced to converge and submerge because of the structure of the waterfall, analogous to how space-time around a black hole is warped so dramatically that all paths are inexorably pulled toward a singularity. The implications of Penrose's work were profound. If singularities do exist inside black holes, then general relativity, our best theory of gravity and the large-scale structure of the universe, is fundamentally at odds with quantum mechanics, the theory governing the subatomic world. This conflict, known as the quantum gravity problem, remains one of the most significant challenges in modern physics. In 2020, the Nobel Prize in Physics was awarded to Roger Penrose for his discovery that the formation of black holes is a reliable prediction of the general theory of relativity. The award not only recognized Penrose's pioneering work, but also highlighted the critical role of singularities and the deep, unresolved tensions between the pillars of modern physics. More specifically, reconciling the colossal scale of the cosmos with the infinitesimal quantum realm. In the annals of black hole theory, one name stands out that has expanded our understanding of these cosmic mysteries: Roy Kerr. This New Zealand mathematician offered a revolutionary viewpoint that forever changed the landscape of astrophysics. Kerr's pioneering contribution was the Kerr metric, a solution to the equations of Einstein's general theory of relativity that describes the space-time surrounding a rotating black hole. Unlike the static, non-rotating black holes envisioned by Schwarzschild, Kerr's black holes were alive, with rotation, reflecting the dynamic, rotating universe we observe. One of the most interesting consequences of Kerr's work on rotating black holes is the existence of the ergosphere. This is a region just beyond the event horizon where the rotation of the black hole warps space-time itself, pulling everything along with it. Here, the very fabric of the universe dances to the beat of the black hole's rotation, challenging our traditional notions of space and motion. In the ergosphere, the laws of physics operate in a bizarre and intriguing way. Particles in light can accelerate to enormous speeds, gaining energy from the rotation of a black hole. This phenomenon fires the imagination, suggesting the possibility, albeit theoretical, of harnessing the energy of black holes, a concept that was once relegated to the realm of science fiction. Perhaps the most revolutionary was Kerr's rethinking of the singularity itself. Gone was the point of infinite density at the center of the black hole. In its place, Kerr proposed a ring singularity, a loop of incomprehensible density and gravity, a concept that extends the boundaries of mathematics. Such a view was not just a mathematical triumph, it was a paradigm shift. In a universe in motion, Kerr black holes rotate, animated by the same forces that rotate planets, stars, and galaxies. So at the heart of our problem is a subtle understanding of the paths that particles in light, geodesics, take through curved spacetime around black holes. The tradiziono idea stated that these paths, both the null geodesics along which light travels and the trajectories of matter, inevitably lead to a singularity, a point of infinite density, where the laws of physics as we now know them break down. However, a revolutionary perspective has emerged in a recent study. Kerr argued that the concept of geodesic incompleteness, the idea that paths in a space-time must end in a singularity inside a black hole, is based on misinterpretation. He argued that while the mathematical parameters describing these paths may be bounded, this does not necessarily mean that space-time itself is disentangled into a singularity. According to Kerr, the paths of light inside a black hole governed by zero-point geodesics could indeed be bounded by the event horizon of the black hole. However, this boundary did not signify the end of space-time or the inevitable presence of a singularity. Instead, Kerr suggested that these bounded trajectories could exist in the complex structure of a black hole without requiring the presence of a singular point with infinite density. Moreover, the Kerr metric introduced the notion of an event shell, distinguishing it from the event horizon, and suggested that trajectories within this shell are affected by the angular momentum and mass of the black hole, allowing for a range of behaviors not previously considered. At the heart of this study is the striking contrast between the Schwarzschild black hole, characterized by a point singularity, and the Kerr black hole with its mysterious ring singularity. This ring, born of the black hole's rotation, stretches the singularity along its axis, creating a structure much more complex than the singular point envisioned by Schwarzschild. The ring singularity of the Kerr black hole opens up a realm of possibilities where the paths of light and matter are not doomed to a singular end, but can loop and twist around this gravitational vortex. This unique structure allows for the theoretical possibility of pathways through the ring, hinting at gateways to other regions of space-time or unforeseen cosmic phenomena. When a Kerr black hole rotates, it traps space-time, entrapping the very fabric of the cosmos. This frame-dragging effect distorts the trajectories of light and matter, causing them to spiral around the black hole, in stark contrast to the straight-line descent to the singularity envisioned in a non-rotating model. In this maelstrom of warped space-time, theoretical models suggest such exotic phenomena as closed time curves, paths that can theoretically return to their past, evoking our notion of time and casualty. Kerr's observations pose a serious challenge to Penrose's theorem. If Kerr's black holes with their singularity-avoiding principal null vectors are more than just a mathematical curiosity, if they are a true aspect of our universe, then the universality of Penrose's theorem is in question. The existence of paths within singularity-avoiding black holes points to a reality far more confusing than a simple point of no return and requires reevaluating current theories. Against this reevaluation, the search for a unified theory of quantum gravity continues as the theory which will organically connect quantum and cosmic. It's infinitesimal and unimaginably huge. And let's hope that now theoretical physicists can breathe with a small sigh of relief, not being so limited by the conventions of space-time singularity.